Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. As I said last time, we want to see how MapReduce can deal with unstructured data. We saw that with text. We'll see how it deals with graphs, and inshallah, in the future, we'll see how it deals with structured data. Before we start, any question about anything in the course? By the end, inshallah, of today's lecture, I'm still thinking whether we switch to Spark or Storm or continue with MapReduce, because I want you to start project as soon as possible, inshallah. I will talk, inshallah, next week. I dedicate maybe 15 or 20 minutes to talk about the project and ideas. I give you ideas about what you can do. Also next week, inshallah, there will be the second quiz. Okay? And always there will be a quiz every 3 weeks. So don't forget. And I don't need to remind you. There will be a quiz every, inshallah, 3 weeks. Okay? Any question about the home? Did you have a look on the new homework? Any questions about it? Any questions? Okay. Later, yeah. Okay. Please start early. Start early. Okay. It needs more time than the first one. The first one was really straightforward. Very few changes, I think. But this one needs more thinking. Okay.
The do part is easy.
Huh?
The do part in the starter code is easy, but the other thing is not easy.
You mean the first homework or second homework?
No, I have a second one.
In the second homework. Okay. Yeah, it needs time, so please start early. Okay. Type. Inshallah, today we'll talk about how MapReduce deals with graphs. Okay, so the agenda is to discuss why we care about graphs, and then we'll discuss two main problems about that involve graphs. The first one is parallel breadth first search, and the second one is page rank. And towards the end, inshallah, we'll talk about some ideas of optimization for graph algorithms using MapReduce, of course. So the first thing, why we care about graphs. Before we say why we care about graphs, what is a graph? I think you are all familiar with this data structure. So graphs is a set of nodes or vertices, and they are linked through a set of edges or links. Okay? Now there are many different types of graphs. First, the nodes and the edges might have other information. It depends on the domain of the data. Okay, so the edges might have weights. Nodes might have some information about the entities that are represented by these nodes. If we are representing people, maybe names, email addresses, and so on. Edges might represent cost, might represent distance. So many different ways or many different types of data can be represented using graphs. As I said, there are different types of graphs: directed versus undirected edges, presence or absence of cycles. Some graphs you will not see any cycles, self cycles, at least. So cycles between the node and itself. Others you might find, it might be allowed. Graphs, of course, are everywhere around us. From the network that we are using, the roads that we are using can be represented by a graph. Social networks can be represented, of course, by graphs. So many data types in several domains can be represented by graphs, even in genomics. Interactions between genomes and proteins and all of that can be also represented as a graph. So graphs are everywhere. Now, here are some of the problems that graphs are involved. You know, of course, when you want to go from one place to another, okay, through the road network, that's of course a graph problem. You need to go to see what is the best path from a specific node to another node. I think you heard about minimum spanning trees before, I think maybe in data structures or algorithms. So minimum spanning trees are trees that are of minimum total cost or weight that links all the nodes in the graph. Okay? Sometimes, as if you read in the textbook, that's a nice example. There is a company that wants to establish a fiber optic network, so it needs to reach all the major places, okay, with the minimum cost, of course. So that's one of the examples of graph problems. Shipping problems, when you want to find the path where you can ship the maximum amount of shipment through. That's kind of problems that's called finding max flow. So you view it as a graph problem, and you want to find the path that can have the maximum bandwidth. In social graphs, sometimes we want to find communities or connected components that will represent closed communities. If you want to analyze spread of diseases, for example, it's good to find these communities and the major key players within each community. Job matching, jobs and people, we have, that's a special type of graphs called bipartite graphs, where we have two sets of nodes, and you want to map from each set to the other. Web ranking, and that's what we will see inshallah today, one of the two examples that we will cover today. How we can use the graph structure of the web to give ranking to pages in the web. And inshallah we'll talk about this in detail today. What is the common theme of all of these problems? The common theme is that all of these problems involve large-scale graphs, big graphs. Okay. Usually, when we study graphs in data structures or algorithms course, we have never thought about the size of the graph, right? We just assume that the graph can be loaded into memory, and then we do whatever algorithm to analyze the graph, right? Here, the problems are much large in scale. Okay, so we cannot assume that the graphs will fit in memory, so we'll have to find a way to scale it up. So, inshallah, today we'll focus on how MapReduce can be used to deal or to analyze graphs. The key idea in using MapReduce for graphs, for processing graphs, as you will see, inshallah, and that will support large class of problems, or graph problems, is to perform some computations locally at each node of the graph, and then share the result of these computations among the neighbors, and repeat that. Okay, so that's the basic theme that you will see, inshallah, today repeated in both problems. So performing local computations and then propagating these computations through the neighbors. When we propagate these intermediate results through the neighbors, this is like traversing the graph. Okay? So of course you heard about traversing the graphs when you studied the topic of graphs before. There are many ways of traversing the graph, of course, but traversing the graph means visiting the nodes of the graph in a specific order. So the key questions that we will answer today, inshallah, are the following. First, how do we represent graph data in MapReduce so that we can do the processing that we want? And how do we traverse the graph in MapReduce? So the representation and the processing questions. So the first one, which is much easier, is the representation. How can we represent graphs? Usually we have two types of representation of graphs. We have the adjacency matrix and we have the adjacency list, right? So what is the adjacency matrix? Yeah, so what will be the rows and the columns in the matrix? Yes, so all nodes will be the rows and all nodes will be the columns, and each cell will represent the edge, if there is an edge between or from the node at the row to the node at the column. So that's the adjacency matrix. Okay? Of course, it can be zeros and ones if we just want to store the existence or inexistence of edges, or it can be the weights of the edges. So it will be 0 in case the edge is not there, or a weight in case there is an edge. Okay? Time. For this representation, what are the advantages and what are the disadvantages?
I think it's too big because you have to represent every node in comparison with every other node.
Yes, if we are talking about big graphs, then this matrix will be huge, right? We are talking about millions of nodes, for example. So it will be million by million. That's huge. Okay, so that's a disadvantage or advantage? Disadvantage, of course. What else? Yes, so many zeros will be in the graph, right? Because even if we have a graph that has millions of nodes, the neighbors of each node will not be in order of millions. Okay? Usually it depends, of course, but usually it's tens or hundreds or thousands. Okay, so in each row there will be so many zeros. Actually, the zeros will be dominating. Okay, and we call that sparse matrix. Okay, so actually very sparse. Usually, adjacency matrix for graphs in typical problems is very sparse. Okay, so that's another disadvantage. Is there any advantage for adjacency matrix? Or it's so bad idea? Any advantages? Look at the rows and columns. Do we have information that are important? And if I want to get the in links, or let's say out links of each node, is it easy to get? Yes, all the ones in the row represent the out links. How about the in links? All the ones in the column will be the in links to that node. Okay, so I can access these very easily. Also, having it as a matrix will allow doing mathematical operations, of course. Okay, that's another advantage. Okay, right. I think we covered. Of course, if it's sparse, then it's wasting space. Okay, we cannot afford having such size in memory and wasting it. Right. The other alternative is adjacency list. In adjacency list, we don't have a matrix. Okay, we have an adjacency list for each node. Okay, the adjacency list will be a list of the nodes that are linked from that node. So, for example, here we have an edge from 1 to 2 and 1 to 4. So we have the adjacency list for 1 is 2 and 4. Okay, so we have to list, of course, the IDs of the nodes that have in links from the given node. Okay, so that's the adjacency list. Now it's no longer a matrix. Okay, for each node we have a list of edges, of out edges actually. Okay, or out links. Type advantages and disadvantages. Of course, the clear advantage is that we get rid of all the zeros. Okay, we don't have any zeros here. We just store the edges in the graph, the actual edges. We don't store the edges that don't exist. Okay, so there's no waste of space here. What else? We have the outlinks. Okay, But it's not easy to get the in links, right? They are not directly encoded here. You have to do some processing to get the in links, right? But you have the out links right away. Okay. Anything else? Of course, saving space. Right? We said that already. So much more compact, easy to compute over out links. These are the advantages. Disadvantages. It's difficult to compute over the in links. Okay? But usually for large graphs, we prefer, of course, adjacency lists. Okay? So we'll keep adjacency list as our representation. Yes. How we process what? What do you mean? You will not be able to do it. If there are some operations that you will have to do, you have to do it at the level of each node. You cannot do it as a level of a matrix anymore. Okay. That's another disadvantage, of course. Okay, now we'll switch to the processing. Okay, as I said, we will have two main problems in today's lecture, inshallah. The first one is single source shortest path, and the second one is page rank. I think you heard about this single source shortest path before. What is this problem? At least you used it, huh? The algorithm?
Yeah,
Traveling salesman. I think it can be seen as a single source shortest path. Yeah. Okay. How can we define it? Not minimum point, minimum path. So we have a source. Okay. So we want to go, for example, from this location, okay, to another location. Actually, the general definition of the problem is that we have one source and we want to find the shortest path to every other location. That's the general problem. But specific problem if we have, of course, two source and destination. Okay. So if you see here, for example, if we are here and we want to reach these three locations, that's called single source shortest path. Type. This problem is, of course, classical problem. Whenever we study graphs, we start the first problem, I think, to be solved is this problem. Okay, so I'm sure that if you studied it in algorithms or data structures, you heard about Dyester algorithm. There is an efficient algorithm to compute this. Have you heard about it? Yes? Okay. Type. What is Dyester algorithm? Let's see this example. We have, let's say that this is the source node, and we want to compute the shortest path from that node to every other node. Okay? And let's assume that the weight on the node is the distance, okay, or the cost. So how the algorithm works? Of course, we will assume for now that the graph is in memory, right? We are not talking about MapReduce yet. Okay, we are talking about just the original Dyester algorithm. The algorithm starts by giving an initial distance to all the nodes except the source node. So the distance to the source node will be 0 because the distance to itself is, of course, 0. That's the optimal. And initially, the distance from the source to every other node will be infinity. Okay? And then we will put all of these nodes into a priority queue. Okay? And then we pick the minimum from that priority queue. So it will be a loop. Every time we will pick the minimum, the one with the minimum distance, okay, from the priority queue that we didn't visit before. So the only one that we have now is the source. Okay, so we'll pick it up from the priority queue, and then we will process the outlinks from that node. So for that node now, we have For that node now, we have how many outlinks? We have one to this and one to that, right? Okay. Now, we will, the current distance from the source to these two nodes are infinity. Okay? Now, for each of these neighbors, we will check if we can reach that neighbor in a better way than the current way. The current way is infinity. Okay? We will compare that with the path that goes from the node that we are visiting now to that node. So the path from here to here is just one edge. It will always be one edge because we are talking about immediate neighbors. So the cost of this is the cost of the source node plus the cost of, or the distance of the edge. Okay? So that means that we can reach that node with a cost or a distance of 10. Now 10 and infinity, of course 10 is better than infinity. Okay? So we will update the distance of that node to 10. Same thing with every neighbor. So we'll see, we'll look at this neighbor, we'll look at this distance, and we'll say that 0 plus 5 is less than infinity, so we will update this distance. Okay? So that will be the first iteration. So after the first iteration, this will be 5, and this will be 10. Okay? Now, remember, this is a loop. Now, the distances, change it for these two nodes, and they are now in the priority queue. Which one is the minimum? We'll pick the minimum, which is the blue one now, and we'll do the same. Okay, now look at the graph and tell me what are the updates that we need to do in the second iteration. We have now 5. We will check all the neighbors. So we have this one, and this one. Okay, so these might be updated. Okay, so 5 plus 2 is 7, of course, is less than infinity. Everything is less than infinity, right? And 5 plus 9 is 14, so that will be updated to 14. How about this one? Will this be updated or not?
8.
Yes, why? Fatma, go ahead. 5 plus 3 is 8, less than 10, so that will be 8. So that will be 8, that will be 14, because 5 plus 9, and that will be 7 plus, because 5 plus 2. And we are done with these. By the way, any node that we get out of the queue is done. We know the minimum distance to that node. Okay? Now, the third iteration, we get to 7. 7, will we update anything? 7 has a link to this, has a link to that. Will this be updated? Of course not. Okay, that's the source. The distance is 0. How about this one? Why?
7 plus 6 is 13.
Yeah, 7 plus 6 is 13. 13 is less than 14, so it will be updated. Now the minimum is this one, and we'll continue. Okay, so 8 to this, of course this will be 9, and 8 to, that's it. Okay, that's it. So that will be 9, and of course 9 will not have any updates after that, so that's it. Okay, so that's Dyester algorithm. It has a priority queue, global priority queue. We pick the minimum every time. We look at the outlinks, and we update the distances based on the local edges. Okay, any question about this? Clear? Okay. Here's the algorithm in pseudocode. Initialization to infinity, except the source to 0. We have the queue. We put all the edges, all the vertices in the queue. And then while the queue is not empty, we pick the minimum and we visit all the nodes. And this is how we use the adjacency list now. We visit every node in the adjacency list, which indicates the out edge. Okay? And we see if D of U is the one that we are visiting now, which is already known about, we know the minimum distance to it. So D of U plus the weight of the edge, is that less than the current value of V or not. If it is, then we will update the value of V. That's exactly what we did. The question is, how can we do that with MapReduce? So it looks very, very nice, right? Very simple. I mean, this algorithm, I'm not talking about MapReduce. This algorithm looks very simple. It should be simple in MapReduce, of course. We'll see. The problem here is that we need to parallelize this. Huh? Yes. The priority queue here, if you start to think about how to look at this algorithm and parallelize it, you will stuck at the point of the priority queue. How can you share this? This is a shared data structure, right? That is accessible. But when you think big, when you think about big problems that has big data, you don't need to really look to the exact sequential algorithm and try to interpret it. Okay? Think in a different way. And you will see that we will not have this priority queue at all. For a simple reason, by the way. We'll talk about it later. Okay? We'll talk about it later.
Is it that the user is going to sort that out?
We'll answer that later. Okay? Right. Now let's think about MapReduce. We will first start by a simplification of the problem. Okay? We'll just assume for now that the weights are ones. All the weights are ones. Okay? And we will relax this assumption later. Okay? So that's the simple case of equal age weights. We'll assume that they are all ones. And in that case, what the algorithm that we will use, or the idea that we will use, is called parallel breadth first search. What is breadth first search? If you remember, every node you visit its neighbors, right? And then you take each neighbor you put them in a queue, and take the first one, visit its neighbors, and then the second one visit its neighbors, and put all of these in queues, right? So it's a traversal algorithm. You traverse in waves, right? You start from a node, and you traverse its neighbors, and then the neighbors of its neighbors, and then the neighbors of its neighbors of its neighbors, and so on. So what we want to do now, or what you will see, is a parallel version of this. That's why it's called parallel BFS, or breadth first search. Right. Here's the intuition of the algorithm. We'll start, if you think about it now, we will start by one node, and if you think about we'll start with the source, okay? What is the distance, what is the best distance of their neighbors? Assuming that we have equal weights. All the weights are ones. There will be one, right? And that's it. Right? So once we reach their neighbors, then we know the minimum, the shortest path already. Right? So for all nodes reachable from S directly, the distance for all nodes P that are reachable directly from S, the distance will be 1. Okay? Fine. How about the nodes that are reachable from these nodes? What will be their distance? 2. Right? 2. So if we are 2 hops far from the source, the distance will be 2. Okay? And so on. So all nodes that are reachable from some other nodes, the distance of them will be 1 plus minimum the distance of their in-links. Okay? So look at now node N. Node N is reachable from M1 and M2 and M3. Let's say that M1, the distance of it is D1. Distance from the source, of course. And distance of M2 is D2, and distance of M3 is D3. Now what is the distance, what is the best distance, or the minimum distance of N? 1 plus the minimum of these, right? If I reach this in 2 hops, then I can reach this through this in 3 hops. But if it happened that this one can be reached in 1 hop only from the source, then this would be the better, right? So the first time, the key idea here is that the first time I reach a node, this determines the shortest path already, or the shortest distance. Okay? But remember, this is only in the case if we have equal weights. Okay? Did you get that? Questions? Okay, we didn't yet talk about MapReduce, right? Just laying out the idea. So it's like waves. If you throw a stone in a lake like that, it will start to make waves, right? So imagine that this is the source node. We will reach, in the first hub we'll reach some nodes, and then the second hub will reach more, and then the third hub will reach more, and so on, until we reach the entire graph. That's the idea of the breadth first search. If you want to visualize it, this is the source node. Let's say that this is our graph. This is the source node. The green ones will be reached in 1 hop. So these are the immediate neighbors of the source node. Then the red ones will be reachable in the second wave, reachable from the neighbors. And then the, I don't know is that magenta or something? I don't know the name. Purple, will be reachable in the next wave. Okay, so this is one distance of distance 1, that's of distance 2, that's of distance 3. Okay? And notice that N7, for example, is reachable also from node 8, right? But of course, the distance through node 8 is bigger than the distance from N1. Okay? So notice that the first time a node is reached, that's it, that's the minimum distance. Only because all of these edges have the same weight. If we change this, that will change, and we will tackle it later. Now, from that intuition, let's think about the algorithm. So we said that the representation will be adjacency list. So that means that in terms of MapReduce, we will have to have key and value pairs, right? So what will be the key and what will be the value? Yeah, the key will be the node, the node ID, okay, and the value will be not the distance, the adjacency list, okay, with the initial distance, okay. And to initialize everything, we initialize all the nodes to be infinity, except of course the source to be 0. Type. Now, what should we do in the mapper? Now think about that. The whole graph now is represented in adjacency list. Each record is one node with its adjacency list. Okay? Yes, the mapper will take a key and value, which is one node. What should we do in the map function now? We want to reach the neighbors, right? That's all what we know. We have only the neighbors, right? And we want to propagate something about the distance. So what should we propagate? Let's think initially, okay? The source node has a distance 0, right? It wants to tell the neighbors some information. What is that information? The neighbors now are infinity, right? They all have the distance infinity. I want to pass my information to the neighbors. For this problem, I want to pass something about the distance. Yes? It will emit 1. Is it 1 generally? No, the weight is 1. The weight of the edge is always 1. We assume that for now. The weight is 1. But will we emit 1 or will emit generally something else?
Should be 1 plus the distance of
Yes, 1 plus the current distance of me. Okay? Initially, of course, the current distance is 0, but we'll have to repeat that. Okay? So each node in the mapper will emit 1 record for each neighbor. Okay? And that record should have 1 plus the current, my distance. What is the meaning of that? What is the meaning of 1 plus my current distance? When I pass it to my neighbor, what does that mean?
Full distance.
Yeah, so that's how I can reach that neighbor through myself. That's the distance, the path from the source going through this node to that neighbor. Okay, so that's what we will have. So for each node in the adjacency list, we'll emit that node and d plus 1. Now, there is one, before we talk about that, okay, forget about this line now. So let's assume that we will emit this. What will happen if we do that? Now the key will be the neighbor, and the value will be d plus 1. What will happen after that in shuffling? All of these distances will be grouped by the node. So that means that in the reduce, I will get the node with distances from the source through what? Through different nodes. Yes, through different nodes. Actually, through the in links. So we use the out links in the mapper, right? Now, we'll see it. Don't worry, we'll see it. Okay. And now the information is coming to me through my outlinks. So the shuffling will group distances by the nodes, and then in the reducer, what should I do in the reducer, by the way? Yani now that, let me okay. So let me try to do this. Okay. Now let's say that we have, this is, remember that we are doing that for every node, by the way. Okay. So let's say that this is node n, and node n has these 3 outlinks to node m. Okay, forget about this. Didn't do that. And m has another n link. Okay. Now, when we process n in the mapper, Reem, can you be with me, please? Okay. When we process n in the mapper, let's say that n now has a distance of 5 generally. Let's assume that n has a distance of 5. Okay. So n will produce how many records in the map function? 3. Okay. So we'll pass. Let's say that this is m1. This is m1. This is m2, and this is m3. So it will generate m1 and 6, m2 and 6 also, right? And m3 and 6. Okay? And that will happen from every node. So all nodes are passing this information. Notice that this is passed through the outlinks, right? Because that's what I know about myself. And when we are processing in the map function, all the information that we know is the map and the node and its adjacency list, right? Which indicates the outlinks. We have no idea about the inlinks. Okay. Right. What will happen is that if we do that through all the nodes, now M1 we'll get, let's say that this is node K. So K also has sent something to M1. Let's say that this is 8. The distance was at K was 8. So K generated also M1 and 9. Right? Now let's assume that this is the whole thing for now. So M1 will have 2 records for the reduce, right? That will happen in the shuffling. So M1 now will get 9 and 6 in the reduce phase. Now notice, where did we get the 9 and 6? Who generated 9? K. And who generated 6? N. What are K and N with respect to M1? The in links. That's what I meant. Okay? So we process the out links in the map, but through the shuffling, what happens is that we got the messages. It's like sending messages, by the way. You can think of it that way. We send messages, each node sends messages through the out links, and then in the reduce, it's like I'm getting the messages from all of my in links. Do we care about that here? Very good, yes. So we can encode that. For now, we are only computing distances. Okay, we'll get to the patterns. Okay, we'll think about that. But let's keep the distance. If I'm only caring about the distance, then this is all what I need. Now, what should I do as M1 in the reduce? So remember that M1 also has a distance, right? Let's say the distance to M1 was 10. It was 7. So what should we do with M1 now? So that means that M1 so far was reachable by 7 from the source. But now I got information that M1 can be reachable by 6 and by 9. So what should we do? Yeah, so we take the minimum, and if that minimum is less than what I have, then I should update my distance. Okay? Yes, exactly. Yes. Okay, so that's only one iteration. That's only one iteration. But it's done, of course, in parallel. Every node is doing that. So every node is passing information through the out edges and then getting the information back in the reduce from the in links. Okay? So the reducer will select. So should I erase this? Anyone want to ask anything? Yes. I erased it.
Information passed from mapper input to reducer as a key will be node with its weight, right?
With the with the distance, yes, with counted. Yeah, that's exactly this line that I skipped. Good point. Okay, so you understood so far, right? So what we will do in the reduce is to get the minimum for each node. Now this is one iteration, so we'll have to repeat that, right? Type. In order to repeat that, that means that the output of this iteration has to be the input to the next iteration, right? Type. So what should be the input to the next iteration? That should be exactly like the input to that iteration, right? How did we start this iteration? Each node with the adjacency list, right? Where it is now, it's gone. We don't have this. Okay? So far, we don't have this. So to keep that, we have also in the mapper to emit the distance to myself. And so this is just to know what I am, what is the value that I had, okay, to avoid putting it in the key. That's answering your question. But I need also to pass my adjacency list. Otherwise, it's gone. Okay? So that means that we are doing two things in the map. Now looking at the pseudocode. We are doing this processing. So the key, this is the key and this is the value. The key is just an ID, and the value is a node which has the adjacency list. So this is a complex structure here. Okay? So for each node in the adjacency list, we will emit this, right? Then the node ID and D plus 1. But we also need to emit this, which is the node itself, so that we can keep the adjacency list for the next iteration. That's of course an overhead. That's a big overhead, but we have to do that. Is this clear? So there are two things that we will emit in the mapper. This is the processing part, which is the messages that I'm sending to the neighbors. And this is just sending the adjacency list to myself, so that I can get it in the reduce phase. Okay? So now, if you remember the M1 getting 6 and 9, right? It will also get its adjacency list. Here's how. You mean in the reduce, right? So in the reduce, among the messages, there will be a special message, which is a node. It's a complete node. So if it's a node, then I will just get the current distance, the current node, sorry, which is D now. So this is M is the node itself. Yeah, that's pseudocode. Yeah, you have to deal with that within the value structure. You had a question, I think?
Yeah, I mean, this first emit, you said it's reused with the mapper within the index iteration.
Yes.
Right?
Yes, so the reduce will pick it. So that will be one of the things that I will get in the reduce, right? So I'll have to differentiate between this, because that's a special value, with, yeah, that's how. So if it's a node, that's of course pseudocode. If it's a node, then we'll just deal with it as a node, which is adjacency list. And if not, then we will do this minimization. Okay, so this node is somewhere here in this list, right? And there's no order unless we order it somehow. So we'll have to check every message that I get through this list, whether it is the node or not. Yes.
And each node has only one passing of the mapper, right? So
each node will have.
What I'm saying, mapper is called only once for each node.
Yes. Yes, of course. This is MapReduce, right? Questions?
In one iteration.
This is one iteration, yes. Yes. So one iteration means one MapReduce job. And once we emit now the node ID and the node structure, now we are ready for the next iteration. Okay? That's this the output of this will be the same graph but with updated distances for each node. Now it is input to the next iteration. Yes. Exactly this. Exactly this. And we will not write any new code. It's just there will be a code in the driver function that will do this loop. Okay? Is that clear? So that we deal with this in a distributed way, if the graph is huge. Of course, there are other more optimized ways of dealing with graphs, of course. It's good also to know how to deal with something like that if you are required to use MapReduce. If all of what you know is MapReduce, then this is how you can deal with it. You will not appreciate or understand the other things until you see how it's done here. Okay. Yes?
How many entries?
Good. Okay. So we'll get to that. So you know now that multiple iterations are needed to explore the entire graph. And we preserved the graph structure already. We discussed that. Now, how many? Stopping criteria. What do you think?
I think we will have to see how many hops are needed.
Okay. How many hops are needed?
Number of nodes.
Number of nodes. Type. Let's. Huh? No, there's no destination here. The problem is one source with all. Type. Let's think together. Okay? We are doing that in waves, right? And we said that once the node is reachable for the first time from the source, it's done for that node. Right? So that means that we will be done with all nodes once we reach all of them the first time. Is that the number of nodes? Okay, type. Let me give you an example here. Let's say that we have something like this. How many iterations we need if this is the source?
8.
8? That's your answer. How many iterations we need? Only 2, right? Because after 2 we reached all the nodes. Why do we need 8? This is the first iteration, we'll reach all of these. Okay.
Because I thought when I asked, is it each iteration for one node?
Of course not. The whole graph. We are doing that in parallel.
That's why I asked two slides ago.
Yeah. Each map is one node, but you know now that map is called for every node. Yeah. Okay. Type. Then what is the answer? Yes, I understand 2, but generally, for this example is 2. Generally, what is the answer? Do you remember there is something called diameter of the graph? Diameter is the longest number of hops between any 2 nodes. Okay, that's actually the number of iterations that you need. You don't need any more than that. Assuming that the weights are equal. Okay, keep that in mind. We didn't relax it yet. Okay, so that's the number of iterations.
If each link carries the weight, then you would need to reach each single node, right?
We'll get to that. Okay. Type. Okay, I think we earlier we said that this 6 degrees of separation. Do you remember? Did we say that here? Do you remember that we talked about something called 6 degrees of separation? Okay, maybe in another class. There is a theory that everyone in the world, if we think about the personal relationships, okay, personal relations between people, if you think about that as a graph, then there is a theory that says that you can reach anyone in that graph in maximum of 6 hops only. Yani I know all of you, right? So I can reach you in 1 hop in the graph, right? I know all of you, and then but you know some people that I don't know, right? That is reachable from me in 2 hops, okay, and so on. The theory says that the maximum is 6. Anyone, from anyone in the world to any other one in the world. Okay, there is, between these two people, there is maximum 5 people. Or 4 actually. No, 5. 5 people. So from me to Trump, for example, there are 5 maximum 5 people. I have no idea, that's a theory. Yeah.
We tested that commitment within the information security industry. We couldn't go beyond 4.
Oh, so it's less than that even. Okay. So that's that's just to show you that it's not that long. So there's no many iterations here to do in order to reach the all nodes. Okay. But that's again assuming equal weights. Okay, assuming equal weights. Okay, two implementation issues. The first one, we said it already, that we need to check outside MapReduce, we need to have this loop, right? Either if you know the diameter of the graph in advance, then you know now the number of iterations. Okay? But usually these graphs are huge, right? So it's not easy to get the diameter of the graph. Okay, so we have to do it in another way. Now, how can we know that we are done?
If you have reached the node.
If I have reached the node, okay? And when can we know that I'm reached?
So the distance will not be infinite.
Yes, once the distance is not infinity, then I'm done. Then this node is done. Type. That means that we want some way to know that all nodes are visited. So we need something like a counter. So we can, at the end of each iteration, we can go through all the nodes and check if their distances now are not infinity or not, right? But that's also huge, right? We have millions of nodes. So there is in Hadoop in particular, there is a feature called counters, and you started to look at that in the first assignment, right? There are 2 types of counters in Hadoop. There is a job-related counters, and this is what you looked at. Okay, the counters that tells you how many input records and how many output records. All of this is done automatically for you. And there are also user-defined counters, so you can define your own counters. Okay, and these counters are per job. So the counter is per job. Okay, and you can just add to it and get the value at the end of the job. So you can use something like that. Once the node has changed its distance, then we increment that counter, and then at the end of the job we just check if that counter is the number of nodes that we have or not. If we got it, then we can stop. Okay, so that's what we mean by the use of counters here. Is that clear? Now to I think one of you raised this issue, I think Reem. Where is the paths? In that algorithm, we just kept the distances, right? Where are the paths? They are somewhere, by the way. I mean, they are there, but we didn't keep them. Yani, think about this. If D less than D minimum, then we will update, right? If I know, as you said earlier, Reem, if I know who sent me this, then this is my previous hop, right? Okay, so that can be sent from the mapper, and then I will accumulate it in the reducer. Okay, so we'll not talk in detail about this, but that's the main idea. You can pass this information from the mapper to the reducer, and you keep track of the minimum path. so far. Okay? So the information is there, but you need to store it. You need to keep it. Okay, now if you want to compare with Dyester, of course Dyester is much more efficient, right? We are doing lots of redundant work here. Can you think with me first, what is the redundant work that we are doing in MapReduce? Yeah, the whole graph is processed every iteration. And in Dyester, we go in waves, right? We visit the node once, and then we visit its neighbors, and so on. Right? But here, every node is sending messages every iteration, because it doesn't know the distances of their neighbors, of course. Right? So that's redundancy. That's a lot of things that are passed unnecessarily.
It should be possible to implement Dyester in the way it works. The way it works, it should be possible.
How? What should be possible?
To implement Dyester in MapReduce, I mean, to eliminate the processing the whole graph each time. If you pass the information that Dyester is passing.
Yeah, but how? You need the problem here is that you need the global priority queue, and in MapReduce there is no mechanism that will allow you to share this. Okay. Of course, we are talking only about MapReduce. There are, of course, other efficient frameworks just for processing graphs. But remember, MapReduce is general purpose, so that's how we can do it. So Dyester, of course, was much more efficient. MapReduce explores all paths in parallel, and that's again why it's called parallel BFS. So we explore all paths. What we did actually is brute force. Is exactly brute force. Okay, we go from each node to its neighbors. And we do that again and again and again and again to explore all paths and all distances. But the actual useful work is at what we call the frontier. The frontier is the actual, when we talked about Dyester, is the current wave. That's where the actual work should be done. But of course, MapReduce is not doing that. The work in MapReduce is done at every node. At all nodes, okay? But the actual work should only be at the frontier, at the nodes that we just visited, we just reached, because that's how we will, or we should pass the information to the next wave. Okay? Of course, we can't do, we can't do better in MapReduce because there is no mechanism of sharing global data structures like a priority queue. Okay, so far we said that we have equal weights, right? Now, any question before we relax this? Everything is clear? Now let's think about the actual problem, which is weighted edges. What will happen if we have weights? So now we will add weights to the edges. You might think, okay, we emit D plus 1 in the mapper. Let's just emit D plus the weight, the distance. And that's it, right?
Yeah, that's it, I think. But the problem is not here. I think it would be when to stop.
Yes, exactly. Okay, so it's the same idea. We will just emit, instead of the 1, we will emit the weight. We also would get the minimum in the reduce, exactly same idea, but where to stop? That's exactly, so it's not it. Okay, it's it about the processing, but we'll have to think about where to stop. So let's look at this nice example. Now, let's say that this is the source, and we reach it P, and then P in the second iteration will reach R. Okay? If we have equal weights, then R found its shortest path, right? But if we don't have equal weights, this path, which looks longer in terms of number of hops, might be smaller in terms of the distance. Okay, so this path SPQR might be better than SPR, just because the weights are different, right? We never know. So that means that the number of hops is no longer the distance when we don't have equal weights. Right? This is clear from that example, right? Time. If that's the case, then we cannot stop by the diameter of the graph anymore, right? The diameter of the graph is computed by the number of hops. It doesn't consider the weights on the edges. So what should we do? Huh? The number of nodes.
You reach each node from source and then you know that that's the way.
Is that the worst case or that's the best case? Yani, the number of iterations will be the number of nodes?
Right.
That's the best case? Yes, see. Okay. To that node only? You are talking about stopping. Okay. So that's now the stopping criteria. If there is no updates in the distances for all nodes, then we are done. But that's not the answer to my question, by the way. But that's the stopping criteria. But my question was how many iterations. Okay. But maybe now we don't need to know in advance the number of iterations. We can just check if there is no changes, any changes in the distances. Okay? We still didn't answer how many iterations, okay? But that's a stopping criteria. Okay? We can no longer stop at the diameter of the graph because of this example, right? If we stopped, we didn't get the minimum of R, and we will never know, by the way, if this is the minimum distance or not, okay, until everyone is done, until everyone is stable. All the distances didn't change. Look at this example. This is one of them. We don't need that, but we have to get a sense of how many iterations, because that's the cost of running that algorithm on a graph, right? And you need to have a sense when, if a graph has million nodes, will we need million iterations? Because that's not practical, of course, right? Remember, in each iteration of MapReduce, this is a MapReduce job, and that means that you will write all the output to disk, which means that writing the entire graph, by the way, right? Right? We will write the entire graph to disk and then load it again in the next iteration. So that's very costly. Okay? So we'll have to have a sense of how many iterations before the distances will be stable, before we get to convergence. Okay?
When you have different nodes in this problem, how it's possible to know this if you don't visit each?
Yes. So So there is no easy answer here. I mean, we will not be able to know really the number of iterations in advance. Okay. And look at this example. There are very bad cases. Look at this example. This distance is 10 Okay, from N1 is the source here. So N6 can be reached by 10, okay, and then N7 by 11, and N8 by 12, and so on, right? So you might think that this is the best, but after some time you will realize that this is not the shortest path, and the shortest path is this one. Okay, so you will need to wait how many iterations until you reach that? So many, right? So many iterations. So the worst case is, the limit is the number of nodes, of course. Okay? But that's the very worst case. In practical applications, I remember, I think in one of the applications that we will inshallah discuss in the second part of the lecture, which is PageRank, when PageRank was done, regardless of what it is doing now, the conversions was, I think, PageRank was done on a graph of the web. Okay, so millions of pages. I think the conversions was done maybe after like 60 iterations. Okay, 60, okay, which is much, of course, smaller than the number of nodes. So in practice, it's not that big. And of course, you can also, if you have a budget in terms of time, you can say I will stop, and that would be the approximation of what you get at that time.
But in that case, you say 60. When it converges.
Yeah, it converged after 60.
So basically, after 60 iterations, there were no changes in weight.
Yes. Yeah, we didn't know that in advance. It depends on the graph.
Yeah. I mean, if you don't reach all of the nodes, how do you know that there's no changes in weight?
How do you? Why do you think that after 60 iterations you will not?
You still need to touch each node in order to know.
Yeah, of course, yes. It happened that for that graph, which was a web graph, it converged after like 60 iterations. Are you saying that it cannot? Oh, yeah, you don't understand?
No, I'm not saying that. I'm saying just that you still, in order to know that it converged, that there is no.
Yeah, we know that after the fact, of course. After running the algorithm, we saw that it converged.
What I want to ask is, in order for our algorithm to know that it reached convergence, right? It needs to touch each node. Because how do you know that there is no changes in cost?
We said that we can do that using the counters, right?
No, I think his point is that even if you don't have changes, you could have changes later.
Oh, no. Once it happens that you don't have any changes, you are done. There is no change will happen in the future.
That's my question.
Yeah.
That was my question, yes.
Yes. And it happened for that example.
You need to touch each node.
Of course, yes. It happened that we reached all the nodes in 60 iterations. Yeah, for that application. Yeah, that's what I'm saying. Yeah. So how many iterations? Of course, we don't know in advance, but the worst case is the number of nodes. But in practice, it is much less than that.